Okay, we'll resume the discussion of high growth areas of the ocean economy. The next topic we're going to look at is offshore wind, particularly as it moves into deeper water. And our speaker for this is Cian Conroy from Principal Power.
Thank you. I suppose I'll start off with a small bit of the corporate presentation on who we are, and really just give a bit of background about floating wind and its opportunity for the marine environment and what we're doing to exploit that. So when we start off, just to give a bit of context, this is one of our platforms being installed off the coast of Aberdeen. The wind float, the Kincardine project, this is our wind float 1. But just to tell you who we are, I think this kind of brings together the different strands of how we are kind of maximising the marine environment. But a small bit about the company. We were founded in 2007 in California, in Berkeley, California, by a couple of petroleum engineers. So our background is very much in the oil and gas sector. And as we move forward as a company, when we look at who our shareholders are, we've kind of got a real mixed bag of shareholders. And again, this indicates where the sector has come from. We've got the likes of EDP, fourth largest renewable energy generator in the world, Repsol, upstream oil and gas, Aker Solutions, oil and gas services company, and ASM, they're a ship fabrication yard in Portugal. So that kind of thing kind of brings together the different strands of the marine environment and shows who we are. We were established, as I say, as a platform developer for the offshore wind sector, and we went through kind of a steep learning curve in terms of demonstration and technology. So we deployed our first turbine in 2011 off the coast of Portugal, which I'll show you in a second. That produced over 17 gigawatt hours, was generation in waves up to 12 meters and survived 17 meter swells. As we go forward in the near term, we're currently in various stages of construction of 100 megawatts of projects across 3 sites in Europe. So we're currently in the process of commissioning 25 megawatts off the coast of Portugal. We have 50 megawatts in construction for a project off the coast of Aberdeen, and we've got further 30 megawatts in development in the French Mediterranean sector. They're what we would call pre-commercial. The next stage for us is to move towards the commercial deployment. So we announced a project a couple of weeks ago in Korea where we're looking to develop 500 megawatts, which, depending on the time of installation, will be between sort of 40 and 50 units. So we're starting to get that stage where our commercial scale. So to give you some context, this is one of our Portuguese projects leaving the dry dock in Lisnave. It's about an hour west of Lisbon. So this was fabricated in a former shipyard dry dock, so we see 2 of them in fabrication. So if you look to the rear of the yard, you'll see a second one that's currently being finalised and prepped for painting. These are towed out and towed to the north of Spain where they're commissioned and then deployed off the coast of Portugal. So, I'll keep going. This is the same unit with the turbine installed. So to give you a sense, these are the largest turbines in the world deployed. So it's the V164, 8.3 megawatt turbine. So who's Principal Power? I suppose really our vision for the world and the marine environment is really maximising the yield in terms of renewable energy sources for the population, the global population. So we can change the world with deep water offshore wind. So to date, the deepest projects we've seen in waters around the UK are at sort of 50 meters, 55 meters water depth. We think by detaching ourselves from that constraint of water depths, we can start to exploit more cost effectively and more readily and closer to population centres for floating wind. So our mission, to make the wind float the most competitive, sustainable, safe, the usual and environmentally friendly platform developer. We develop these solutions with our partners. So I was asked there at the break, are we a developer? The short answer is no. The piece we're responsible for is the actual hull. We design bespoke to the conditions. We design the hull and the mooring system. We work with our partners to develop that. So whether it's any utility developing commercial scale projects around the world, we work with them on that basis. So that's the corporate spiel. I mentioned our project. This is the Windfloat 1. So this was the world's first semi-submersible floating wind turbine. We deployed it as a 5-year demonstration project off the coast of Portugal. So we deployed in 2011, funded by the European Commission under the NER 300 programme, New Entrants Reserve, decarbonisation. So what we did here was we took a standard Vestas V80, which would be an onshore turbine at the time. We fixed it to the platform, and we deployed it at a former wave test facility off the coast of Portugal. So we operated 1 year, return period 7 meters sea states. We endured, what you see there is a 17 meter wave coming over the bow, 30 meters per second wind speeds. The turbine performed remarkably well. And just to illustrate that, where we look at the bottom, the curve is the power curve, and that's really how turbines are rated in terms of their power production, in terms of wind speed and power. And what this graph shows is, this is the power curve from a conventional Vestas V80. So when we look at an onshore turbine, any location, we've mapped over that the power production curve of the marine one. So it's about that, we're to pretty much match the sea state, the performance on an onshore turbine with that with an offshore turbine on a floating platform. The whole purpose of that demonstration, and why 5 years, these turbines are designed for a 20-25 year design life, was really to show the concepts of, when we build these platforms, we commission them in harbour, so we don't use offshore construction. I'll talk on that in a second. But then it was also to show the operation and the performance, and here we have our power curve. And the final part was actually to show how we decommission them, and that's another key element. So to decommission and maintain these, we unhook them, return them to port, and they're decommissioned using onshore cranes and so on. So that 5 year cycle was really all about showing the life cycle. So it was an accelerated life cycle in a very extreme condition, and to go through all the various iterations of commissioning, decommissioning, and operations. So when we move forward from that, I think when we looked at the power curve, we showed it could work, we showed we could build them, we showed we could deploy them, we showed we could maintain them. We then went to the commercial scale. So that's really where we've been working towards. So since 2011, we've been making incremental steps. But I'll hopscotch back a wee bit and talk about why floating wind. I think the topic today is on maximising the marine environment. So this is just what is the wind float and why we can use it. So where the wind float can operate is we can what we would call transitional and deep water sites. So as I said, to date in the UK, the 99% of the projects deployed are using monopiles structures as fixed. We then use jackets for sort of intermediary depths into 55 metres. What the wind float can do is start to untap or unlock those untapped resources. So we see projects in Scotland, and I'll show some of those in a second. These are sort of ranging from 55 up to 150 metres water depth, where a conventional fixed bottom structure won't be able to operate. The wind float, as a floating structure, we can start to deploy in those water depths in the transitional zone, so from 45 to 55, but then go beyond where fixed structures can. We can go to the best locations. So what we've seen in terms of the higher capex of the structures, we can deploy these platforms in windier locations. So as I said, we sustain 30 metres per second wind speed. We look to 9 and 10 metres per second wind speeds off the coast of the west coast of Scotland. We can go where the wind is, so we don't need to be constrained by seabed, so we don't look for sandbanks, which the existing round 3 sites we're looking at. We can go where the windier sites are. From the health and safety perspective, our offshore works are minimised, so we use pretty much standard oil and gas practices, but we use kind of quite health and safety. So we do all the commissioning on the quay side, so the turbine is installed on the quay wall using onshore best practices, onshore crawler cranes, health and safety is controlled. The platform is then towed to site where the anchors have been installed, pre-installed in safer weather conditions, and it's hooked up and operated. So it's really about reducing the need for human intervention offshore when we move away from, say, fixed wind farms. Economies of scale, the larger wind turbines, I suppose this really is where we start to see the real benefits of the wind float, is that the crude metric is megawatts per ton of steel. We're not constrained by the size of the turbine. So our first platform was a 2 megawatt turbine. Our next platform, we installed an 8.3 megawatt turbine. What we've seen in that example, our mass of our substructure increased by about 1.7 times. Sorry. So it's not a linear progression from a 2 megawatt to an 8.3. We're scaling at about 1.7 times. Our next project will be to 9.5 megawatts. It stayed the same scale. So we've nearly gone from 5 times the power output to 1.7 times the mass. So from our metric of power per ton of steel, we're starting to see bigger and bigger. We're now working to the stage. We announced this week our project in France will be using the 10 megawatt turbine. So at that stage will be the largest turbine ever deployed on offshore, but also on a floating structure. And we're in development phases now for projects around the world with 12 megawatts. And what we're seeing is that rate of sort of increase in mass is slowing down, so we're probably going to cap out about the same rate. The weight of the substructure, it'll vary by sea stage and site, but that megawatts generated to ton of steel will stay pretty low. Minimizing the impact on the seabed and marine life. So because, again, when I talked about fixed structures, these are piled into the seabed using various methods of piling. We don't require that. Our preferred solution is drag embedment anchors. So again, we're minimizing our impact on the environment. It can be withdrawn after the 25-year lifespan, so there's negligible impact on the marine environment. So it's about more sustainable deployment. Key other driver is, I suppose, energy security. Where we've seen countries with aspirations for offshore wind, the UK has been very fortunate to date in that the southern North Sea is relatively shallow, and that's where we've seen the greatest deployment of fixed wind is in that sort of 25 to 30 metre region. Where we have countries that are looking to see more and more renewables with our targets, the UK with their 75 gigawatts. It doesn't have that, the southern North Sea isn't an infinite resource in terms of space, so we need to look to other sites, west of Scotland, north of Scotland. This is where we're getting into particularly deep waters. Countries like Spain and Portugal with especially deep waters, the west of Ireland, again we're looking to 200 metres water depth. These countries have very stringent renewables targets but don't have the means of deploying offshore wind. We're seeing more and more constraint in the onshore wind market, and solar will contribute significantly to the renewables target, but it won't be able to meet all of that. So floating wind is that bridge between the aspirations of governments and the ability to deliver that. I mentioned the wind speed, so the high load factors. So we're seeing, the highest load factors. So the Vestas V80 I mentioned is probably the highest, best performing Vestas in the world in terms of that deployment and capacity factors, because we can go, as I said, where the wind is. And then also cost competitive, and that's a key driver. The key driver across all the renewable sectors to become to cost competitive energy. We can't be putting more and more costs onto the taxpayer or the bill payer. So when we start to look to scale, as we're at the demo stage at the moment, and these might be deemed as more expensive, we're going forward, we're starting to see cheaper and cheaper projects. And then when we go to these markets where they don't have the shallow waters, the costs start to stack up in terms of installation vessels, heavy lift vessels, jackups and so on. We remove ourselves from the need for that. So again, our cost competitiveness, we start to be able to deliver large scale projects at a very cost competitive rate. And then I suppose, crucially, I don't need to kind of restate this, but just to talk about the climate change. We've seen lots of figures mentioned in manifestos in the last week about increasing our ambition for 2030 to 40 gigawatts of offshore wind. And the UK with an ambition to go to net zero by 2050, the modelling suggests that we need about 75 gigawatts of offshore wind just to meet our net zero. So that's including the build out we have to 2030, but we'll start to lose sight. So that rate of deployment, we need to increase that rate of deployment to achieve that. So what floating wind brings us is an immediate solution. We can bring these projects to market quickly. We can do serial production and achieve greater scales and deploy them in greater markets. Disruptive technologies are needed for that. I think what we would say is, and then the suggestion on that 75 gigawatts, when you talk to the Committee on Climate Change, we don't need any revolutionary technologies, we need disruptive technologies, and this is about bringing existing marine technologies together, and that's what we've done. We've taken the oil and gas and renewables. And it's that type of approach we need to be able to bring together disruptive technologies. And the final piece, I suppose, is I've mentioned this already, but it's about enabling offshore wind to reach its full potential, to deploy in those markets where it couldn't have deployed before. So that's the background. I suppose the bit in the current room is to talk about the technology. Here we see a schematic of the wind float. So, as I said, the technology comes very much from the oil and gas sector. So what we have here is pretty much a scaled down production platform. The wind float, when it was designed back in the early 2000s, was developed as an auxiliary platform for the oil and gas sector to be able to enable more space on platforms that were constrained. Due to its scale, the developers started to look at ways of stability control, and they incorporated the active ballast system. So the active ballast system marked A in the picture, that's really about bringing the platform into trim. So in response to the high wave conditions, we were able to move water. There's a sealed water system between the three columns, so we were able to move the ballast around the three columns. So it's a double redundant system. Each column will have 2 pumps with a unidirectional system. So we have more than double redundancy in that regard. But that is there to be deployed and keep the turbine stable, and that enables us to get that power curve that I mentioned at the start. We can keep the turbine at a level state, so we can get the power production, and I suppose crucially, we don't impact on the reliability of the turbines. We take turbines from the existing offshore sector, so they have quite stringent warranties on them and performance guarantees. We're able to keep those by ensuring the stability of the platform. The other element we see at section B is the static water ballast system. So we have 2 ballasts. This is the sealed static system, so we pump water during the commissioning phase. So when the platform leaves the dry dock, it's empty. We bring it to its commissioning port, we start to ballast the water. We ballast that in a controlled state, so as we start to add the weight of the turbine, we need to counterweight that with the ballast of the water. Once the turbine is installed, it's brought into complete even keel, and then it's towed to port. We can adjust that ballast for a number of reasons. Where we deploy in limited water depths, we need to allow the ballast to raise up over constraints. So to move it out of the dry dock in Portugal, I think the draft at that point was 4 meters. So these platforms are 2,500 tons. We're able to drag it and move it over 4 meters by adjusting the ballast. When we deployed off Dundee in Scotland, there's a sandbank at the entrance to the Tay. We had to adjust the ballast to get it up over the sandbank, to then deploy it off the coast of Aberdeen. And that's the kind of key element within that. Going on to the D, I'll come back to the next piece, C, but the D is the third element that enables us to keep static in the water, and this is using our water entrapment plates. So these are the plates at the foot of the column, and they use the passive water system, so the weight of the water in response to the thrust of the turbine to keep it in station keeping. And this is the main ability of the platform to station keep is these water entrapment plates. So you'll see 3 of them, 1 on each column. These differ based on the site-specific characteristics, but it's a key element of the technology. The final piece, the turbine agnostic, and this has been crucial to our success. In the offshore wind sector, the revenue is determined, and the electricity is determined by the turbine itself. The platform is a secondary consideration. It's about your ability to generate electricity. It's a truism, but that's so. What we've taken the view from the very start is we couldn't design the platform to be turbine specific. It couldn't just be in response to one turbine. So whether it's a two-bladed or a downwind system, that will create its own bottleneck in the market. So what we do is we respond to developers and their preference for a turbine. So we have worked with every turbine manufacturer, those that existed and have merged. So at the moment we have big 3. There's Siemens, Vestas, and GE. We have the ability to work with any of them, and we've certified and done pre-feed and feed with those, so we can work across the board with any turbine choice. So I think that's the key piece for us, is that we don't need to constrain ourselves to that. So just showing you some of the examples. Here we see the Windfloat Atlantic in construction. So this was constructed over 2 yards, two shipyards, Lisnave in Portugal and Ferrol in the north of Spain. These were a major milestone in the floating wind sector. They were the largest turbines of their class, so we used 3 8.3 megawatt turbines. We had them in 100 meters water depth. We were certified by ABS. Crucially and uniquely, it was the first floating wind farm in the world to be project financed. So that's brought us from that demonstration and sort of low TRL into the world of sort of commercial finance. And we're able to bring in, I suppose, strong institutional investors and utilities. So the likes of EDP I mentioned, Engie, the French developer, and Repsol as well as the developers in that project. That is currently going through commissioning. So here we see the second yard I mentioned, that was developed on a quayside and skidded off into the water. So that's about 2,500 tons of steel that's skidded on SPMTs. It was then brought out and submerged, and the tugs brought it offshore, where we in turn commissioned it. Our next project is the Kincardine project off the coast of Aberdeen. That's currently under construction at the moment in the fabrication yard to be deployed next summer. Once that is deployed, that will then be the largest floating wind farm in the world at 50 megawatts. And again, we're pushing the boundaries in terms of rated capacity. Each turbine will be 9.5 megawatts, and we will deploy it in water depths of about 60 meters on average across the site. And then thirdly, our last is the EFGL Gulf to Lyon project in France. So France has made a strong aspiration for floating wind and has a commercial licensing round in development. We have secured one of the sites in the Mediterranean, and this is where we've started that evolution of the platform. So the first was the pilot and prove the concept. The second then really is the industrialization, and that's really where we're at the moment, is that industrialization. So the consortium has changed. We've brought in EPC contractors, the likes of Eiffage, but again, we're looking at serial manufacturing. You'll see schematics. We've changed our fabrication process and our weight. So that's me for a second. I'll shut up and let something better cover this. This is a video we produced for the Wind Float Atlantic, and this really shows the potential of floating wind, but also the process in the background.
This is a new way of generating energy, and an important step to fight against climate change. Portugal enters in a new era with an international acclaimed solution in the production of offshore renewable energy. The Wind Float Atlantic project, formed by a consortium made up of EDP Renewables, ENGIE, Repsol, and Principal Power, is the first floating wind farm in continental Europe, just off the coast of Venezuela. This floating wind farm will allow the optimization of natural resources and will speed up the commercial deployment of this innovative technology. Wind Float Atlantic is an example of a more sustainable future for mankind, with the largest turbines ever installed on floating platforms. The total installed capacity of 25 megawatts will provide sufficient energy to 60,000 people throughout the year. This energy promises an endless source. The potential of wind is immense, and this renewable energy is an essential part of the worldwide decarbonization strategy, free of CO2 emissions. The Wind Float Atlantic project is the future we envision. Our mission has begun, and we will continue to nurture the power of nature to make our planet more sustainable. Wind Float Atlantic. Energy beyond the horizon.
Give me a break. I suppose just quickly, just to close out, just two last slides, really is the potential we see in the UK here. So there's currently a process underway in Scotland for commercial leasing rounds for floating wind, which will be launching in January of next year. You'll see the site. When we look at that, 60% of the sites that the Scottish Government will be leasing are in water depths of 60 metres or greater. So that's probably, using our conservative estimates, using those sites in the upper map, that'll yield about 3.5 to 4 gigawatts of electricity in that 60 metre plus area. And we would expect to see about a gigawatt of that in construction development by 2030. So the opportunity is growing at a pace and scale. And then finally, we see the further water depths, so it's the Crown Estate for England and Wales. The map on the bottom was a map developed by DEC showing water depths of 100 metres and greater and wind speeds of 9 metres per second. So basically the southwest and the northeast of England are the main opportunities when we go forward across the rest of the UK. And finally, I suppose the supply chain. We've started to really kind of industrialise the supply chain, but bring the learnings from other marine environments. So from the oil and gas sector, existing companies that you'll be familiar with, the likes of JDR, from the umbilicals and risers in the oil and gas. First Subsea in Aberdeen, we've used them quite a key piece for our supply chain. But then we also use the onshore sector to develop that. So it's really about adapting the supply chain and bringing that into the commercial scale. So I think I'm spot on.
Great, thank you, Cian. We have time for a few questions. Maybe just one or two.
Thank you. So I'm from the OC. One short question. You mentioned for the Portugal turbine that there was you couldn't notice any negative impact on the seabed and on ocean. What about the impact on marine life?
In what regard?
Well, on turbine, well, in terms of disrupting, I mean, sound? Did you see any impact?
So-
Did you measure it?
So because we didn't have any piling, so in the fixed industry there's quite extensive monitoring and mitigation systems for piling noise with bubble curtains and noise mitigation. During our installation, it's a standard drag and bed with anchors, so there's minimal noise in that stage. During operation, they don't produce noise. We've monitored. We had during that 5-year cycle, we had acoustic monitoring, and there's no meaningful noises generated from the turbine.